Let's take a look at an example problem for ME 111 from Module 9. So the problem we're going to take a look at here is example 9.2.2. It's for an underdamped system, the response with two complex roots. This is an underdamped case with a second order system that has two complex roots. So in the problem statement, they tell us the model of a certain system is given to us by this equation here. Our 6x double dot plus 12x dot plus 174x is equal to 15 f of t. Now there's two parts to this problem. The first part, they asked us to obtain a steady state response for f of t equal to 5 times the sine of 7t. And in part B, they want us to obtain the expressions for m of omega and our phi of omega. So now that we've had a chance to read through the problem statement and understand what they're giving us and what they're asking us to solve for, our next step is to create our setup page. So again, we're doing an example problem 9.2.2. And for our setup here, this is going to be the response with two complex roots. So we're given the 6x double dot plus 12x dot plus 174x is equal to 15f. We're also told that for part A, f of t is equal to 5 times the sine of 7t. Now they want us for part A to obtain the steady state response for this f of t equal to 5 times the sine of 7t. And for part B, they want us to obtain the expressions for our m of omega and our phi of omega there. So as we begin our solution here, we can reference back to our problem statement and our setup page for any information we need to plug in. So we have our general equation here given to us in the problem statement, our 6x double dot plus 12x dot plus 174x is equal to 15 f of t. So this is a second order model. And the form here, mx double dot plus cx dot plus kx is equal to f of t. Where for this case here, our m is going to be equal to 6, our c is going to be equal to 12, and our k is equal to 174. So now for our transfer function, t of s is equal to x of s over f of s, which is equal to, in our case we can see down here, from equation 9.27 in our text, 1 over ms squared plus cs plus k. Now if we plug in for our specific problem here, we see that t of s is equal to x of s over f of s. Plug in for our m, our c, and our k from up above here, m, c, and k from that general form there. So t of s from our transfer function is equal to 15 over 6s squared plus 12s plus 174. But we recall now, before we move on, that we're dealing with for part A, they give us f of t is equal to 5 times the sine of 7t. So for the next part of our solution, we have our general equation. I rewrite it down here. Our 6x double dot plus 12x dot plus 174x is equal to 15 f of t. And our transfer function here, our t of s, is equal to 15 over 6s squared plus 12s plus 174. So now what we can do is we can go over to table 9.1.1, and for the frequency transfer function, the transfer function t of s, with s being replaced by our j omega here. Now, what we need to do next is figure out what is our omega here, so we can go to section 9.1.4. So we can see in this section here, we have f of t is equal to a times the sine of omega t. Now for our input for this specific problem, we are given that f of t is equal to 5 times the sine of 7t. So from this relationship here, and referencing back to 9.1.4, we see that a is equal to 5, and our omega is equal to 7. So if our omega is equal to 7, we can plug in over here, and we're plugging into our frequency transfer function here with our omega of 7 right there. So therefore, S is equal to 7J. So we'll rewrite our transfer function here. T of s is equal to 15 over 6s squared plus 12s plus 174. Now we can sub in the s is equal to 7j, where we had our omega that we solved for with our 7 from our given function f of t. So we can come down here and start plugging in. So we go to our main equation up top there, and we plug in everywhere there's an s. can plug in a 7j. So we do that there. T of our 7j is equal to 15 over 6 times 7j, quantity squared, plus 12 times 7j plus 174. Well, we take this, if we square this right here, we end up with a negative value right there. So we have negative 6 times 7 squared plus 12 times 7j plus 174. We can reduce and simplify a little bit more. So our t of, when we replace s with 7j, t of 7j is equal to 15 divided by negative 120 plus 84j. So now we can go to our amplitude ratio equation, which we can find on table 9.1.2 in our text, or equation 9.1.5 in our text, where we have m for our amplitude ratio equation here is equal to the absolute value of our t of j omega there, which is equal to 1 over the square root of 1 plus omega squared tau squared. So now we can plug into this here, and we can say, okay, m is equal to, in our case here, absolute value t of j, 7 times j right there when we plug in. So from this here, what we can do is plug into the right-hand side of the equations. This now becomes 15 over the square root of 120 squared plus 84 squared. So when we do this here, we end up with m is equal to 0.1024 for a value for m. But we're also going to reference back to this as well, especially our denominator here as we go forward with our calculations. So the next thing we need to find is our phase angle. And we can find our general equation for our phase angle from equation 9.1.6 in our text, where phi is equal to the angle of t of our omega j, which is equal to negative angle of 1 plus j omega t, which is equal to the negative inverse tangent of our omega t. And we can also see that simplified version on table 9.1.2 from the second equation in that table there, where phi is equal to negative tangent inverse tangent of our omega t there. So now we can plug in our known values here and find that phi is equal to the angle of t of our 7j, which is equal to the angle 15 minus the angle of 120 minus our 84j, which we again was from our previous slide there. For our values there, we can see as this is equal to 0 degrees minus the angle of negative 120 plus 84j. So we could have used this relationship right here as well. And we need to realize with this here, for this angle right here, if we're talking about our real and our imaginary parts of this equation, we're going to be in our second quadrant here, because this is a negative 120. So if we look at a coordinate system down here, you can see, okay, in the top right here, there's my coordinate 1, coordinate 2, coordinate 3, and coordinate 4. So if I'm talking about going over negative 120 on my real axis to this point right here, and I'm talking about going up 84 on my imaginary axis right here for j, I end up with this relationship here, where my angle from this axis over here is going to be my phi right there. So what we can see is this is phi is equal to my negative pi plus the inverse tangent of those two components right there, negative 84 over 120. So my phi value, when I do out my math, is equal to negative 2.531 radians. So next, I wanted to find was my steady state response to this here, so we can get this relationship from table 9.1.2, where my steady state response here is equal to b times the sine of my omega t plus phi in general form, where see that my b is given to me as a times m. This again is from that table 9.1.2. My a I'd found to be 5, given to us. M we solved for, this is 0.1024. My phi I solved for was negative 2.531 radians, and my omega we found to be 7. So we have all the information we can plug back up into this equation here. When we do that there, steps here, we can see that our steady state response is equal to 5 times m, which is there, it's my b right there, because my b is a times m, my a is 5, times the sine of 7t plus phi. Now I know I have all these values here, I can start plugging in some more. So my steady state response is equal to 5 times, I plug in my value for m of 0.1024 times the sine of 7t plus my phi value here of negative 2.531 radians. Plug this in here and I see that my steady state response is equal to 0.512 times the sine of 7t minus here 2.531. So that's the answer for part A. Now we're moving on to part B, where it asks us to obtain the expressions for m of omega and phi of omega there. We're also going to plot these as well. I'm going to show how to do the solution in MATLAB. So we're going to replace our s with our j omega again for this thing here. So we'll do some skip steps within this because we've already gone over it in part A. So what we end up with here is our t of our j omega is equal to 15 over 16 times omega j when we replace our s with omega j, plus 12 times omega j plus 174. We can reduce and simplify this a little bit. We're squaring that j there, so we get a negative 6 omega squared plus 12 omega j plus 174. What I've done here is my imaginary parts have a j in it, so there's my imaginary, my real parts. Here I've underlined in red. So I can combine and simplify a little bit more. So my t of j omega is equal to 15 over 174 minus 6 omega squared for my real portion and plus 12 omega j for my imaginary part there. So from here we can take a look at equation 9.1.5 again here. So we can come up with our m of omega here is equal to by 15 over the square root of 174 minus 6 omega squared, quantity squared, plus my 12 omega j squared there. So m of omega is equal to 15 over the square root of 174 minus 6 omega squared, plus, when we simplify this down, 144 omega squared there. So now we can go to equation 9.2.9, where m of omega, which is one of the things that has to obtain, is equal to 20 times the log of our m omega from this relationship over here, where our m omega, we can copy that over. It's given to this here that we found previously from equation 9.1.5. So now we recall the general rules for a log when we're doing with a quotient here. So log of some function m over n, or some fraction m over n here, is equal to the log of the numerator minus the log of the denominator. So we can plug into this relationship here now. M is equal to the 20 times the log of, and then there is this function here from above there, 15 over the square root of 174 minus 6 omega squared, quantity squared, plus 144 omega squared. So then we can use our little log rule here and say that m of omega is equal to 20 times the log of 15. Do some simplifications here, minus 10 times, get rid of that square root there, of 174 minus 6 omega squared, quantity squared, plus our 144 omega squared for our m of omega, which was the first thing that they'd asked us to obtain in part B. So the next part of our solution, we're going to look at our phase angle here. So we have our relationship that phi of omega is equal to the angle 15 minus the angle here from our denominator here of 174 minus 6 omega squared plus 12 omega j. So for our 174 minus omega squared greater than 0, we have the relationship here, the negative inverse tangent of 12 omega over 174 minus 6 omega squared. And for our 174 minus 6 omega squared less than 0, here we have our relationship here. It's the negative inverse tangent of 12 omega over 6 omega squared, when that's 174, minus our 180 degrees. So another thing that we could do is we could have solved this all in MATLAB, and you can see my code over here for my script file there in order to solve for these. And you may need to change or play around with your omegas, your a's, in order to get the correct m's, b's, and your angles here. But what I used this for was to plot out our magnitude and phase plots. So I used this function right here, where my omega here I set up from 1 to 100, and we did this here, and you can see for our system function here, system 1, by that function there, we were able to get this, and you can get a visual here. If you don't put that semicolon at the end there, then you can actually see what this is, make sure that is correct. That is correct what we did by hand, as well as our continuous time transfer function. And you can see when this plot that provides over here on the right, you can see our magnitude and our phase there, and our shapes here, and again it goes from our 1 up to 100 there.